This is the last talk of the spring semester of What Physicists Do. I'm thrilled. I don't have any kind of wand or scepter to give to Dr. Tom Target, but he will be running the series in the fall, and so we're excited to see a new set of speakers come in and a kind of a new perspective on it, so we're all excited about that. This is, I think, going to be a wonderful talk. No pressure. This is a wonderful talk here to be the final talk of this semester, because we have Dr. Zahid Hussain. He's a division deputy in the area of scientific support group at the Lawrence Berkeley National Lab. He studied at Stanford and received his PhD from the University of Hawaii. He has had a distinguished career in condensed matter physics. And we'll be talking today about the myriad of energy science experiments made possible by the advanced light source. This is the U.S. Department of Energy synchrotron facility, and it provides users really around the world to the brightest beams of soft X-rays in the world. Just sort of as an aside, this talk could be from your work and the varied work and the published history over 500 papers, is probably even more than that, of Dr. Hussain. This could be a very technical talk, and what Dr. Hussain does as a deputy director, he sees a lot of different experiments, and he just showed me today a pamphlet made up to let people know the variety of things in a particular field, energy science. So this talk could be any one of his specific expertise in depth, but instead, I think very nice for this group, it will be a broad survey of the kinds of science enabled by this amazing resource that we have so close to us here. So let's all give a warm welcome to Dr. Zahid Hussain.
Okay, thank you very much, and I was so delighted to hear that you had initiated this seminar series for the last many years, more than half a century. And it is a wonderful thing that when I received the invitation from Dr. Scott, and I was wondering that should I go there, because one of the things is that it's a lot easier to give a seminar, which is the expertise of your science, and because you pick up your old view graph and all you do is put together and put some new ones and done with it. When you want to give a talk which is such a diverse community, it actually is harder. Okay? So I had to do a little bit extra effort to put these view graphs together so that you stay in touch what I'm talking about. So what I will be telling you is about energy science and what we could learn by using these light which come from the accelerated electron, various kind of accelerator. And I will tell you why you like to use these accelerators to get the light. And this light which we are talking about cover a broad spectrum of energy. So the outline, so before I go there, most of you have already seen it, but this is what the advanced light source is. It used to be a 184-inch cyclotron. Until 93, it got converted into a synchrotron, and now there are approximately 2,500 scientists throughout the world come and utilize this annually, and we publish more than 1,000 papers per year, and it is free of cost. All you have to do is write a proposal, be competitive, and then you could come and do the science. So you are welcome to come over there. So the outline of my talk is very simple. I give a broad, big picture why we are doing this class of science, and then I explain a little bit about what are these light sources, so you understand why we have to spend money to do these kind of things. And then I go through few examples, and through examples it's not easier to explain that how one could utilize these kind of system to understand new aspect about various problems which we face in energy sciences. Some of them are so fundamental, at the same time it is not understood. I would say there are a couple of things which I pointed out where whoever solved the problem is Nobel Prize there. Okay? So it's that class of science, all right? Always very simple. So the bottom line is that if you like to understand any complex problem, then what do you need? You need some kind of tool which gives you a higher sensitivity and higher precision. That's all you like to get to it. You like to do better than what everybody has done, not only in a thinking wise, but also the way you detect the signal. You see it better, okay? And sharper, you see more clear. So, Department of Energy has basic energy sciences, and the way they set up the roadmap is that they define various grand challenges. These are the scientific problems which are out there, and we need to tackle them. So, unless you put these kind of buzzword in your proposal, you're not getting a funding. Okay, so remember that. So the way it was started, the first report came in 2007, and those are these red part of it. And then over the period of 10 more years, so they further added new aspect to that grand challenges. So if one look it over, energy and information on the nanoscale is right there. You have, and these circle where I pointed out, these are some of the things which I'm going to touch upon when I'm going to make my presentation. So I will try to cover many of these things. And without spending too much time here, I'm going to get to the real part. So first thing, the 20th century was the century where we were doing a lot more observation science. We are looking at the thing and saying how it happens. 21st century is going beyond that. Not only we are observing things, we like to control them. To be able to control them, we like to understand and we like to design material to have the properties which is the ability to see, and to be able to have the properties what we want. What is important that we should be able to see the functionality of the materials relevant in time, and the time could be down to femtosecond. The femtosecond time scale is when the electrons hop from one atom to the other atom when the bonding takes place. It is as fast as that much. The length scale down to nanometers. These are the interatomic distances are of the order of few angstrom. And quantum confinement takes place of the order of few nanometers. And energy down to millieV, and that's the precision at which you could see the energy scale. Room temperature is 25 millivolt. So you like to go much below that. And to be able to do that, what we like to do is that have the develop the tools where we could use the inner working of the matter down to the level of electrons, spin, atoms, and molecules. So we have to go to the fundamental level to be able to understand that. So one important part along that line is that you have a 3-axis, which is your space. This could be spatial information also, imaging and all that. You like to see dynamics, which is time. And you like to see the energy scale. That's how everything happens with energy. Things don't just go by itself. Dynamics, every aspect. There has to be somewhere energy. That's how the process takes place. Okay. If you look at all the condensed matter physical, general physics, pretty much it comes down to 4 important aspects. You have a charge, you have a spin, you have lattice, and the atom could have its own orbits. So if you go down and look at that these various degree of freedom which exist, how does the material properties evolve and how we utilize them? It arises because of the interaction of many degree of freedoms. So they interact together, and I give you example in a simple way. A transistor makes use of only one aspect of the property of material, and that is its charge. And we have silicon, and we have a silicon technology next door, and you see how much revolution came up with that part. you make the effect of the transistor pretty much you dope the materials, and you have some field effect, and this is exactly what develop everything which you see, computer, everything else, right? You do it a bit more, and you add spin to it. Now you can start recording aspect, or you have a information which you could control. If you go a little bit more and add another orbit to it, the spin orbit interaction leads to what is known as topological insulator. Topological insulator is a new class of material which came up in the last about 7-8 years, which are bulk. In the bulk, they are metallic, and on the surface, they are semiconductor, or they are insulator. So imagine that what the future is going to be is going from the simple computer which we have today to the computer which are quantum computers. So one aspect, maybe I'll come to that particular part later on, and I'll explain to you that today's computer, just a year ago, they actually have the same computing power as they surpassed just last year as a mouse has. The only difference is a mouse uses 1 watt of power and does that same computing as a supercomputer which uses 10 megawatts of power. This is the level of technology at which we stand today. So when quantum computer comes in, and they anticipate that maybe in 2025, the supercomputer will have the computing power which will be equivalent to our brain initiative. Okay? We are not there yet. Okay? So then comes to an aspect that where more than 3 degree of freedom, it could be spin, charge, lattice interact together, and this is what is known as emergent phenomena. You could dope a material, and that material could be insulating. Without the doping, when you dope, it becomes a superconductor. So high temperature superconductivity is one of the phenomena which is unsolved. Still, we do not really understand that this material, one of those is copper based, copper oxide, you dope them with the material, they become superconducting. Higher superconducting temperature is about factor of 2 off from the room temperature. It will be revolution if somebody make a room temperature superconductor like that, and we still do not understand the mechanism.
Dr. Hussain, can I ask you for context on superconductors? Because throughout my life, I've heard about the push towards room temperature superconductors. Is this ultimately like energy storage becomes no problem at all, or is there still other issues? Like if we have room temperature superconductor, the idea was you don't lose to dissipative heat. Right, but I never looked enough into it to know if like this is a tenable solution for power storage, for the grid or something, or whether there are other breakdowns in that.
So right now, actually, in the New Jersey and New York, they already have a liquid nitrogen based power distribution. They already tested that. So they use the superconductor, but they have to cool it down in the tunnel with a liquid nitrogen. So imagine that. If it is a room temperature, it means that we could have a power which is distributed over the whole country without anything. And more important, which I consider to be that imagine that all transportation system which use the magnetic field, if it is a room temperature superconductor, it's extremely easy to create that field. And because once you create, it's not dissipating. So that field could allow you that you could have a transportation is much cheaper. Right?
Right.
Not only that, even these MRI and all those things, if you are superconducting, you could create a lot more field from that one without cooling anything. And the point is that in every school there will be MRI there. So the guys sit down and he had a little injury, they check it out right away.
So people would have,
there is so many technology you could develop with it.
With room temperature superconducting, one of the quadrants here of the kinds of study, the way we have to deal with medicine, the way we deal with transportation, the way we deal with energy is transformed. In a way,
absolutely. Yeah. You cannot even imagine right now. Right, absolutely.
Thank you.
Okay. So what do you like to do? Whenever you are doing this thing, your point is that you like to understand the to go down to the fundamental level. And that's what will be my purpose to try to explain, okay? All right, so let's say that first of all, so light. So the one property of the light is what we call it as brightness. It's say flux density of the light. So the flux density of the light, what is on the say X-ray, which we take in the dental X-ray, or what is the flux density at the surface of the sun, there is a certain unit. And remember this one, this is logarithmic. It means that every dot is 10 times more. So as compared to what you could produce X-ray in the lab, which is we're taking for our body X-ray or dental X-ray, by utilizing these X-ray-based light sources, you could get about 1 billion times more photons, which means get that many more X-rays. It means you have enough intense X-rays that you could probe the material properties by enough of the intensity, so you could go and see the material itself down to that level. If you go from that part, you could go to free electron laser, X-ray free electron laser. The first X-ray free electron laser was at Stanford. It just lays like 7-8 years ago. The first experiment when the lasing process was done, I was a graduate student at that time. It took that long until they built up an accelerator. So remember, see the allocation. Now, there are certain ways of defining how much intensity comes out. Intensity comes out is intensity of the light which is coming out from these proportional to the number of electrons in the storage ring. So if you put a number of electrons in ampere, then we know that there is lots of electrons there. So that many photons will come out. If you make undulators, and wigglers are another kind, then there is a new term which adds up, which is square of the number of poles. So you have a lot more intensity. That's why there's 4 order of magnitude higher, 1, 2, 3, 4, 5 order of magnitude higher. And if you go to free electron laser, they bunch the electrons so close together that when the light is emitted by one electron, it interferes with the next electron, and the effect is a square of the number of electrons. And since the number of electrons would be 10 to the 10, the square of the number of electrons, you could get a gain of 10 order of magnitude from that. And that is what is known as free electron laser. So free electron lasers are so intense that most of the time you have to think of an experiment which is such that you, in the process of looking at it, you do not disturb the properties. Or you do some measurement, what you are looking for, your measurement is done before you destroy the sample. And I will show you the example. Okay, so how does the X-rays are produced from electrons? And you already know that. Because in a radio transmitter, there's nothing more than electrons going up and down from the needle which stick out on the pole. And when the electron goes on up and down, that's what is essentially producing the radio waves. So you control the way the radio waves are produced through your transmitter. In the case of synchrotron radiation, which is one way, or the free electron laser, exactly the same thing happens. The only difference is there the energy of these electrons are billions of electron volt. It's a relativistic effect. Instead of light going all around, right? It is very much pointed on the tangent direction, and all the photon comes like a laser. So my laser is very pointed. That's how the light comes. But it's X-ray light coming up. That condensed rather than going all around like my sound, right? Sound going all around. It's not like sound. It's like a laser, like that, but in X-rays. So if you look at one aspect, we know that the computer is such a revolution. And the Moore's law is that every 18 months, the computer speed doubled. In the case of a brightness of the, so it doubled. And it turns out that in the case of a synchrotron, this is the computer power, and this is the synchrotron. And synchrotron doubles a triple every 18 months. So their increase of the brightness even faster than the rate at which the computer picked up the speed. So you could imagine that it is extremely revolutionary. Yes?
Wait, are you saying the computer, for Moore's law, increases
slower than, huh?
It's double in 18 months, and then.
Double every time, every 18 months is double. That's known as a Moore's law.
Okay, and then the SR one, it triples.
Triple every 18 months.
But that's with the X-ray brilliance side.
Yes.
Okay.
So then there's one is speed, the other is brightness.
Okay.
Right.
Thank
So,
you.
so the point is that the rate of improvement or gain is even more because we know already that computer went so revolutionary development, right? That even the light sources, their brightness has gone even faster than that. So that is amazing thing to realize. Okay. So just to be on the same page, what is light, right? So we have infrared. Synchrotron produces light from here all the way here. So we have a synchrotron, infrared. So there is some experiment which are carried out in the infrared also with the synchrotron light. You could produce also infrared in the lab, but the one which you produce in the synchrotron has some characteristics which are much better than what you could produce in the lab. Okay. Then you have a visible part of the spectrum. Then you have a ultraviolet VUV, extreme ultraviolet, soft X-ray, which I will be covering a lot more. ALS is the word. ALS gives energy or photon from here to here, but they are the world leader for doing science in this area of spectrum, soft X-ray. Okay, and I'll show you why soft X-ray. Okay, and then you continue with the hard X-ray. So this is the spectrum we will be using. Only a small fraction is visible; the rest is invisible. Of course, I have to feel. That's all. Okay. So before I'm going to start now my aspect that how we use these tools to do spectroscopy. So one of the most important tools which we use is photoelectron spectroscopy. Many times we call it photovision spectroscopy. It has many names, and some of that you have probably studied in your class. It's known as electron spectroscopy for chemical analysis, ESCA. That was the start. Its name nowadays a lot more common. It's the same thing. It's the different names, okay? Now it is a lot more common. The same thing is used like more like a X-ray photoelectron spectroscopy or XPS. And you probably have heard that name for sure. And I'll show you why this is useful. Another one, if you do and look at the valence electron, is a technique known as angle-resolved photovision spectroscopy. So you study the electronic properties of the materials. Okay. So let's go and see what that really does and how you use it. So before I start, I'm starting, say, go 200 years back. Okay. So the first thing which was determined, and that was Young's experiment, 1803. He found out that if you take a light bulb and you put slits, then when the light goes from one slit and the other slit, it interfere together. And you have a diffraction, interference pattern. So what does that really mean? It means light is a wave. So that was set in concrete. Like the words of God, light is a wave. Okay? What happened? 100 years later, Einstein came in 1905 and to explain a photoelectric effect, which means when you shine a light, the electron comes up, to explain that aspect. He had to use an equation which showed that the kinetic energy of the electron which comes out is equal to the incoming energy of the photon minus the energy it takes to get the electron out from the material. This simple equation, when you put it forward, this is just a conservation of energy. People didn't believe it. Say it's wrong. Why? Because already it is said that light is a wave. This is trying to say that the light is more like a particle and cannot be true. Light is already, Young's experiment has already shown it's a wave. How much it was deep-rooted in the mind of the scientist. The H here is a Planck's constant. That scientist, 1930, so it means 5, right? 8 years later, even, writing a recommendation letter for Einstein, made a statement which, okay, a statement where he's saying that, look, believe Einstein is a smart guy, give him the fellowship. Don't take it against him that he has such a stupid idea of saying light is a particle. And he got the Nobel Prize from here. He didn't get the Nobel Prize from theory of relativity. This was his Nobel Prize. So remember that a simple aspect to change the mind of the people many times, it takes huge amount of effort to convince the scientists that look, whatever you are thinking, this is the way we like to tell you is a different kind of thing. So now the same physics continued, and this is what we study. So what we do, if you take a material and you shine a light on the material, the electron get popped out. It has to be in vacuum because in the air they will just get scattered by the air and they won't go anywhere. So you have to do the experiment in a vacuum. So you have some kind of detector, analyzer, which picks up the distribution of the electron, and you determine something, what you do. So to be able to observe any properties, how could we observe? How do I see you? The only reason I see you because light hits you and reflect, and my eyes are a detector, and I see you reflecting light. So I could see your feature, I see your color, I see everything. Exactly the same thing happened in our material science or physics. To be able to see any properties, we have to interact with the materials, get something out, and from that observation and measurement, we determine the properties of the material we are looking at. So look at, a material has, as we know, have electron, 1 s2, s2p, all those electrons. So there are core electrons, call them core electrons, which are closer to the nucleus. Then there are valence electron, and then there are unoccupied, which is known as conduction electrons. So we shine the light, we knock these electrons up from the material with enough energy, and we measure the energy distribution of those electrons. All we do is we measure this energy distribution. We don't know inside the material, but we use the Einstein equation, which is a conservation of energy, which means the energy of the incoming photon is the kinetic energy plus the binding energy. From there, we could determine the properties of the material. Let's look at how we determine the property of the material. Look at acetone. So we do not know, acetone is there. It has carbon atom, two kinds. One is red carbon, the other is the other carbon. We don't know in the material that it is actually red or green. Then there is an oxygen. If you take a spectrum and you look it over the spectrum of the carbon, what you see two peaks instead of one. But you see two peaks, and what happens that they are not in the same energy position, they are shifted. So it means this carbon has a different chemical bonding as compared to this carbon. This is hydrogen and this is more electronegative. So it means doing these class of experiment, I could understand the chemical bonding. So that's the aspect. So we are going down to the level where we could say that it is red peak is half as big as the green. It means there are twice as many atoms of green in the molecule as it is red, because you can see that one carbon is that color, right? And so from these properties, and then you see that the oxygen comes totally different place. So it means that if the material has many elements, I will be seeing many elements independently. Which elements are there? So I could determine its elemental composition, I could determine its chemical state, I could determine it through a quantitative ways. How many? So that is the tool I have in my head. And I could use it for whatever I like to use it for. So I will show you how we could use it for. So if you have a state like silicon and it oxidizes at different state, then it means that you have multiple peaks of different oxidation states. So it means that you could understand the chemical nature of the material by using this tool. Okay? Now, let's apply it. So one of the most important problem is our fuel cell. So what is a fuel cell? Actually, the car already exists. You could buy a car which is based on hydrogen fuel cell. And what is the process and what it utilizes? In a fuel cell, the process is very simple. Your hydrogen is coming to one of the electrode, which is anode. There is another electrode which is cathode. In between is some kind of membrane which is your electrolyte. So when the hydrogen comes in, that's your fuel. The the hydrogen has to break up on this electrode. Well, how does it break up? It is a catalyst made of platinum. It breaks up the hydrogen into ions, protons, and the electron comes up. They take this electron, let it go through the load. A load could be your automotive engine, the motor there, right? You take that electron, goes to your car, and the proton has to come and combine and complete the circle. Without that, it won't work. You have to make sure that the process goes, right? So what do? Then the oxygen from the air comes in, and we have to break up the oxygen, and it has to combine with ion, and the product is water. So here you take an hydrogen, combine with oxygen, make water, and you run your car. And what a wonderful process, right? The wonderful process, yeah.
I'm kind of confused. So does the oxygen move towards the cathode, then the load, then the anode, while the hydrogen moves the other way?
The hydrogen is going through the membrane, the proton, ions. Electrons, which are stripped out, they are going through your motor.
Okay, so the
So they run the
electrons-
electricity is motion of electrons. There's nothing more than motion of electrons, it's electricity. Right? But these protons has to combine with something else to make a product. And the potential has to be right? There's a voltage has to be driven. So then what is done is that it is the combination of hydrogen plus oxygen making water. That's it. So now, but it uses something. Why it is like that? So let's look at it a little deeper. So what you are doing is, you have one on the anode, there is a hydrogen oxidation process. So what is happening? Hydrogen gas is coming, it's forming the hydrogen ions plus electrons. It's stripping that one, and it is happening on the surface of this anode. Okay. If you go to the other side, it is the oxygen combining with proton which came through the electrolyte or membrane, and the electron which came through the load on the other side combined together to make the water molecules. But where this reaction is taking place, even today's car actually, this reaction is taking place on the surface of a platinum. Do you know platinum is more expensive than even gold? So why can't we think of other material which could be better, and it could be cheaper and better? It turns out that this oxygen reduction reaction, the reaction which takes place oxygen, hydrogen, electron to make water, is 4 order of magnitude slower than this part of the reaction. So why can't we make that 4 order of magnitude higher, and then we have a lot better efficiency? So I have to go a little faster. What you need to do is that, first of all, in the case of anode or even auto, what you like to have is that the reaction such that it's neither too weak and not too strong. If it is too weak, the interaction doesn't take it. If it is too strong, hydrogen will just get stuck with the platinum, never come out. You don't want too strong either. So you have to balance all those sort of things, okay? So I'm going to move a little faster, and let's look at it. So this is the outcome. So one of the research which was done was that why don't we combine platinum with nickel? And the outcome of that research was that they were able to make platinum and nickel act as an electrode 90 times more active than the state-of-the-art platinum catalyst. So 2 order of magnitude gain is an extremely good gain. So why that happened? It is spectroscopy. I haven't shown the spectra, but I will show you the physics what went in. What happened that when there is a pure platinum, and when you have a platinum molecules comes in, oxygen, it is the, remember that, it's the oxygen reduction part of the reaction, okay? Oxygen comes and it has to combine with hydrogen. Intermediate state is OH radicals. This OH radical go and get stuck on the surface of platinum and occupy sites. When they occupy sites, more of the hydrogen and oxygen don't have the site to go there so that it could make a reaction. combining, considering that platinum is just too reactive, you want to balance it. They mix with the nickel, which has similar kind of electronic structure as platinum, but make it a little bit of you could just make it a little slower, okay? The result is OH radical doesn't bind to the surface as much. When the intermediate state is come there, it just kind of come up. So the result is that more site is available and your reactivity goes up by that kind of factor. So a simple physics of combining hydrogen and oxygen to make water is suddenly now is a new physics, new knowledge, new understanding. And even today, when we talk about these things, these are the kind of physics we talk about. I took a very simple example, and this was a science paper in 2007 done by our lab and our scientists at one of my beamlines. Okay? All right, now we move on. All right, so here comes, before I explain that one. So the part is that to be able to do any science, many times you get stuck with something. All these experiments you mentioned has to be done in vacuum. And the question is that in realistic catalysis and all that one, real conditions are not vacuum conditions. You like to build up your instrument which is closer to what is actual working condition. So and the effort was done by scientists in 70s when I was a graduate student. This is the guy who got Nobel Prize in 80s, okay? And he just couldn't thinking about, he thought about many things and couldn't think about what is the good solution. It turns out we came up with a solution which was that instead of just putting orifices to develop a differential stage, put lenses in between so the electron, instead of just hitting the slit side of the walls, could get focused through the slit and get to the detector. Result was 1,000 times higher detection efficiency. And outcome is a new technique which is commercialized. We got R&D 100 award, and there are many systems which we do right now we are using. And we pioneered this technique and we lead the world. Okay, new class of science. What is the outcome? The outcome is one of the first experiments which was done. If you take another bimetallic catalyst, which is a combination of rhodium and palladium, very common in the industry utilized. It turns out, depending on the oxidizing state, either it's oxidizing state in the atmosphere or reducing atmosphere, atom between the core and the surface exchange itself. Nobody knew that part. So the result is that there was something which was not even understood, that when this catalytic reaction takes place, the surfaces get restructured, atom moves back and forth, all that kind of new things happen, and you cannot take a model compound under idealistic condition and say this is the reaction which is taking place in the industry. No. The real things are very different from what you make as idealized conditions. So you need to think of instrumentation which enables you to do that class of science which is closer to realistic conditions. The outcome was this tool. This tool, unfortunately, cannot be built in the lab easily. People are trying to do it because it needs very high brightness, and that high brightness comes from these kind of light sources. Okay? Now, emergent phenomena. What is an emergent phenomenon? When you say 2 plus 2, what is it? 4. But in science, there's many times 2 plus 2 could be infinity. Now you say it's crazy, right? Imagine a material which is totally insulator. It's insulator, nothing passes through. You dope with another element and it becomes a superconductor. The current just passes without any resistance. Zero resistance. You change the property from one to the other just by adding doping. That's known as emergent phenomena. So why emergent phenomena takes place? Let's think about it this way. Let's say there's a bunch of apple on a tree. If you want to understand the properties of the apple, what do? You pick one apple and you could explore it, open it, see how sweet, how sour, whatever it is, right? But let's imagine that this is what we call it, the system is uncorrelated. You know, each one has its own properties and you could study that without disturbing the body clock. If the system is correlated, you take a bird, bunch of birds there, shoot one, the rest of them react to it. And you do not know at a priori what is going to happen. Just by looking at this bird, I cannot tell what are the rest of the bird doing. I have to see the composite picture. And that's exactly what happened in quantum mechanics. So you have a 2-electron system, then these 2 electrons interact together. You could write down a Hamiltonian which determines the properties of that material very well. When many electron system comes in, you have to add a correction terms. And that correlation terms is the one which leads to all this complexity. Understanding and trying to extract the information, that's where it is important. So we need to understand what property comes in. I'm going to show you a very simple example. Okay, so there is a new class of material known as 2D material. Graphene was one of them. Now they are matter dichalcogenide, molybdenum diselenide, molybdenum sulfide, and one of that class of material we studied, which I'm going to show you the example, is tungsten diselenide, which has one very unique aspect, which has very relevant for energy sciences. Okay, so you could make this material in the lab. You don't need synchrotron to make the material. Remember, you could do it in the lab, your lab. You combine various kinds of, so you develop various kinds of heterostructure, do many exotic things. I don't have a time to explain to you some other aspect, but you could make a bunch of good stuff. Okay. One of that stuff we prepared, and before I get to that one, is the properties of molybdenum disulfide. Molybdenum disulfide, selenide, all they behave same way. So what was known, and here's the surprising thing: if a material is bulk, its fluorescent yield, photoluminescence is very low. It's like flat line. If you make it into few layers, it goes up. You make to single layer, it goes even lot higher by order of magnitude. How come a material, when it is thick, doesn't do as good a job as it start getting to the level that it is single layer? And the physics behind, we measured that one. 2014, we had Nature Nanotechnology paper to explain that part. Okay? So what is that one? If you take a material, now this is little physics. So don't excuse me for that one, but it's valence electron and conduction electron. That's all we are doing looking at. Valence electron and conduction electron in the momentum space. Okay? So this side is momentum and this side is energy. I didn't put energy scale. This is some energy scale. These are valence electrons. It turns out when the material has many layers, like we prepared 8 monolayers, it has a top. You see these lines? These are the electrons which are present in this material. This is the top of the electron. That is where the highest energy electrons are in the material. And then in the conduction electron, the electrons are here. This is momentum space. One is here, the other is on the other side. It means that in the momentum space, they are different places. You have a band gap which is of the order of 1 eV from here to here. So the silicon has a band gap of 1.1 eV, by the way, okay, as a comparison. So you have a band gap and then you have one here, one there. It is known as indirect band gap. Whenever absorption takes place, for the light to go in and absorb, a silicon exactly happens the same thing. It has to do 2 things. It has to do energy conservation and it has to do momentum conservation. Energy conservation you could do with 1 eV, easy, because the solar spectrum is like that. But momentum conservation has to go through scattering process in the material. If somehow this material could be a direct band gap, which we could do by making from 8 monolayer to single monolayer, where the top of the band, renormalization of these electrons takes place in the material, and suddenly the material become a direct band gap. Now this process is a lot easier. All you have to do is conserve your energy. Momentum is already conserved because it's right vertical transition. And this material is a lot better than silicon by far. If you make a solar panel out of this material, it will be far, far superior material. So these are the kind of technology. It could be a very good photodetector, or you could make a photovoltaic devices which are much, 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 much better. It could be flexible, it could be all sorts of new things. Okay? Alright, keep moving on, right? Okay. Multimodal approach. So you don't do the science with one kind. You have to combine many aspects together to get a comprehensive picture, to understand the whole physics. All right, car. Yeah, now everybody love to have it. More, and you know, automobile which doesn't take any gas. Okay, so the physics-wise, just simply speaking, Tesla utilizes 100 kilowatt hour of energy capacity the battery pack. You know, it costs about $57,000 just the battery pack in the Model S, and they don't make any money. When they, if you buy $70,000 Tesla, you are pretty better off because they are paying money from their pocket to give you the car. Okay, so you are very Model X, Model 3, which they want to sell for $35,000. They are trying to use economy of scale. They build up a big plant. They are hoping that they could reduce the price. They still do not know they will make money initially. But what does that really mean? It means that I do not really have a time. I could tell you nice stories about it, about the batteries, but we are today in a primitive stage of battery research. There was a big breakthrough when lithium-ion battery came as compared to nickel metal halide. And that was a huge quantum jump. And that revolutionized lots of things. Okay? And there our future is improving the batteries for the lithium ion. Zinc air is another part. Lithium sulfur is another part. Lithium air is going to be the eventual, they say maybe 30, 40 years from now. And remember that these are relative. So you could be that much better from where we are today, you could be here. It means, but I always joke that if you could make the same battery pack, same amount of quantity wise, you put that one in one charge, you could go from here to Washington, D.C. It would be revolutionary. One charge. You don't have to stop anywhere. Okay? So, there's lots of research which is going on, and I'm going to give you some example of it. Okay? So, that's how the battery works. You guys don't need to understand. It's once again to electrode. Ion goes. Okay? This is, one part is what is we call it as a anode. The other is cathode. When the charging takes place, all the lithium ions are in anode. There's a graphite which does that job. And when when you are using the battery, which means that it goes to the car, then all the ions are on this one. When you go and plug it in and charge your battery, then the electron goes towards this side, and ions also migrate to that side. That's how the battery works. That's how we do back and forth. We charge with our power and use it, right? There's a certain voltage involved, certain number of electrons involved that determine the total power. So it turns out you need about 8 atoms to get one lithium at anode. It's graphite. And it turns out instead of lithium, if you use silicon, you take one silicon and you could put 4 lithium. So imagine that instead of graphite, if we could use silicon, then we could be a lot better by order of magnitude. Okay? And why don't we do that? There is certain chemistry involved. And the chemistry is structural chemistry, another aspect of it. I don't have a time because I want to explain, show you something more cool, but I'm going to show you a little bit of that. These are some techniques in addition to photoelectron spectroscopy, which I explained. There's another technique known as X-ray absorption spectroscopy, X-ray emission spectroscopy. There's a YouTube. You could go there and look at it. Okay? So I'm going to skip that. But here we show spectroscopy. If a material, if this is the cathode, if there is a lithium iron phosphate, and lithium is all saturated, the spectrum looks like that. One side is the iron 2 plus, the other is iron 3 plus. Iron 2 plus is much stronger peaks than the other one. This red spectrum is like this. And as you change the delithiate, then the spectra keep changing around. There are too many spectra together, okay, it's difficult to see. But eventually, when you go to the fully lithiated, then the spectrum looks like blue color, like that. Knowing how the spectroscopy feature changes, we could see a material is lithiated or delithiated or intermediate state, and we could understand and follow their reactions. Okay? One of that, to be able to understand the conduction of the electron was, and I'm going to just tell you the result, that the scientists were able to make the anode pattern by a factor lithium-ion battery, which I have in my packet in my iPhone. 7 times better at the anode. Missing is you have to do the same thing at the cathode, and that's still missing. If you combine both together, you have a revolution. Okay? Alright, photosynthesis. I'm coming to the end. So photosynthesis is an extremely important process. We would not exist here if photosynthesis process hasn't started. The earth, when it was created, it has a lot more nitrogen. There was not enough oxygen. Microbe developed, and photosynthesis process started from, and oxygen enrichment took place, and that's why we have 20% oxygen on the surface of the earth. That's all it was. How does this reaction take place? Would you believe we do not know it? And the first person who is going to solve that problem, photosystem 2, is a Nobel laureate, no doubt about it. And what is the reaction? And now I'm going to explain to you. Okay, so this is a movie. This is using free electron laser. I'm going to show part of it.
You're probably familiar with photosynthesis, the process by which plants, algae, and other related organisms use light energy to convert carbon dioxide and water into sugars and oxygen. This incredibly important multi-stage process is not only responsible for providing most of the energy necessary for life on Earth, but also for maintaining the oxygen in our atmosphere. Now, using the high-energy X-ray laser pulses produced by SLAC National Accelerator Laboratory's LINAC Coherent Light Source, scientists at Lawrence Berkeley National Laboratory, in collaboration with scientists at SLAC and Stanford University,
Okay, so the lady
and
who's
collaborators
behind
in
this one
Germany,
is this one
Sweden,
Nobel
and the
laureate.
UK,
Okay,
have
I'm going
developed
to skip that.
powerful-
I'm going to skip that, okay, because we need to get to the real stuff. Let me show you what it is, okay? So what the process is that in a plant, you have a complex proteins. One of that protein aspect is what is known as photosystem 2. Okay, so this is the complex protein. The photosystem 2 does only one thing. It combines 2 water molecules with an oxygen, combine 2 water molecules and break it up so that you have an oxygen molecule, 3 oxygen, and 4 hydrogen ions and electrons. That's all the reaction is. If I understand that reaction, I'm a Nobel laureate. Okay? So the latest experiment which came in Nature just about a few months ago actually, was to understand in the material of the leaf there is manganese atoms which does this catalytic reactions. It goes through 4 photons absorption through a cycle which are 5 state, S0, S1, S2, S3, S4 in a certain time dynamics. And the current understanding is that somewhere here and in this reaction, the reaction breaks up the water molecules. There is a controversy. Japanese scientists think it happens here, and the US scientists think no, it happens right here. And they're one of the intuitive, I was talking with one of the scientists, and he was saying that, look, if it was happening in nature, would never need its 2 other steps. Okay? His one of the reasoning was that it has to be like that. And they did spectroscopic study. How did they do that? So I get to that one. Okay. So they combine both crystallography, which determines the structure. A crystallographic experiment determines the structure of the material, and a spectroscopy which determines the chemistry. See, X-ray photoelectron spectroscopy is spectroscopy. When you do X-ray diffraction, that is structural properties. They combine both properties together, multimodal, to see at the same time what is happening there. So they use the certain pulses of the light, which is coming from X-ray free electron laser. They're trying to explain what synchrotron and that does. Okay. They combine the X-ray diffraction and spectroscopy on the same system. One problem. When the light hits this photosystem 2, the first shot, which is every 7 millisecond, 8 millisecond, this is 8 millisecond, there is a pulse of photon comes and hit the sample. The first time when the photon hits, the system is totally destroyed because there are too many. So what they have to do, they have to take all the information before the molecule is totally decomposed. So what happens? Before this molecule is decomposed and lost all its characteristic, they already have taken diffraction and spectroscopic sample in femtosecond $1 billion. The new upgrade is about $1.2 billion. Okay, so that's the magnitude of scientific activity to understand water. Okay, the experiment is done. They take the diffraction and all that, and I think that's not really, you know, at the end just leave it. That's what they're studying. Okay, so I like to come to the end. So here is my concluded slide, and you can read it. And this is to encourage you guys. There's plenty you can learn. And there are a bunch of people I use the view graph from to make it so more general. I do condensed matter physics, and ARPES, superconductivity, is one of my field of specialty. That's it. All right, I stop here and thank you for your attention.
Before 5, so let's try to get a couple questions in.
Yes.
Yes, in the front. So the cool thing is we're talking about spectroscopy.
Right.
This is not how you expensive. Like, how do you get this data? It's coming in so quickly. It's like it's only lasting a little while. Like, I'm just wondering, it's only lasting a little bit. How does the computer even handle all that information? That's just short here.
Okay, so there are two parts. So the information which comes, the first short one here, say it's a 0 prime, and you got the experiment data came out in the detector plane. It could be a photographic even film. Okay, so when that data came through the photographic film, that doesn't have to be fast. It just take whatever time take. But what you have to make sure that before the second shot comes in, you stop in between, so it doesn't overlap with the previous data. So that's how these experiments are. Every shot is 8 milliseconds apart, and we could read it out in 8 milliseconds, the whole detector, into another information before the next shot comes in. It's a shot by shot readout. The content of the information which comes in is huge, terabytes of information, and that is where there's lots of effort, and we are spending tens or hundreds of $millions to make sure that we could store all that information. And one of the idea is that don't really keep all the information there. Think of method. You analyze before you store the data. So you add built into those, you could say that machine language is the machine learning. So you optimize your experiment. Don't keep all the information because you will never be able to digest it.
Yeah.
Okay, you will be spending the whole life to analyze one data set. What you like to do is to figure it out ways of picking up the right kind of content which is useful for the problem we are trying to solve. That's what it's done.
I'd like to make a quick comment, which hopefully will get you to respond as if it's a question. But what I saw with the material on understanding photosynthesis phase 2 or whatever.
Photosystem 2.
Photosystem 2. I'd heard of this, and then we didn't quite understand how it works. And just even looking at the pictures, you see how complicated these molecules are. Just to see how this is. So I knew there's sort of some fundamental interest in how this is done, but in your talk, I feel like it's very much connected to that fuel cell. You know, one of the ways that there's this fuel cell economy is if you talked about catalytic reactions and being able to increase efficiency by 90 times, basically needing to use less than about 1% of the same amount of platinum. If you use that, you can still build the same number of engines or catalytic converters. But when we're talking about this, is it really the idea that if we can reverse engineer that process, we're going to put sort of that biological understanding into fuel cells? Will our energy production, you know, be somehow more organic than it is now? Is that the idea?
No. But they are related. In the sense, see, the nature is very simple. One leaf, when it does a reaction in the morning, is much more reactive than about noontime when the sun is up there. Because if it is same reactivity as in the morning, it will burn itself. It knows how to turn it off. Many natural processes which takes place, as you could see, you have water molecules, you break up the water molecule to get oxygen. but at the same time, the hydrogen and the electrons go and combine with CO2 from the atmosphere and make a sugar in the plant. That's where the sugar is. Grapes, sugar comes from that. It is a combination of ions combining with CO2 and electrons. That process I didn't mention even that one. It turns out, you could say simplicity wise, a hydrogen, which we could produce by just breaking up the water molecules, and we could produce lots of it, is a very good fuel also for car. And the reaction is, sound like opposite that, but the reaction there is platinum, reaction in the leaf is to the manganese. And there is also calcium here. So so what is happening is that whatever the chemistry is going on in the nature, if you could just understand that, even 1% of it, our knowledge is not there even 1% of it, we could develop so many things which essentially will be the kind of thing which already are completing the cycle in the nature. See, nature didn't destroy itself. It evolved itself to just continue doing the same thing. We are destroying. We are producing too much CO2 in the environment. Okay, there's no doubt that there is more CO2 in the environment than it was when we started, human beings started this activity of technology. Let's say that. All the combustion engine and all the petrochemical thing. So, it is similar kind of chemistry, and one word which science will use, learn from the nature to develop artificial processes. So there is a learning from the nature, but developing something which is useful for running an automobile. Yes,
Very
has
good.
a value.
Well, after a 90-second break for anyone to move quickly and quietly out of the room, a few of us will stay for some more questions. Let's thank the speaker. If you need to sign in, can you take this out to the table outside there? And start the sign in on the outside. Thank you. Are there, the sign-in is out there. Are there any high school students? I'll be out to stamp you in just a moment, okay? Please step outside.
Don't put that away. There's a slide I want to ask.
Yes, sure. I can show you, bring the slide to you.
You had a monolayer and then 8 layers of
Yes,
silicon and the band gap.
and it's a molybdenum diselenide
Yeah.
material. Yes.
Well, they may be interested too. but-
I should. Right there. If you want, I can show you there. But
Yeah,
You want
yes,
to draw
it's
on the
better.
screen?
Okay,
let's
we go back. We go back.
Go back to that.
Back to the screen. Okay.
Yeah.
It's easy to put it.
So can we restate the question maybe for the camera that's still rolling?
Well, I haven't asked the question. Silicon has a band gap of 1.1
EV.
roughly,
Yes.
and that corresponds, you need a certain energy photon to excite it. Now, in that single layer, it looked like the band gap got up to 1.8 or 1.9 EV.
Yes.
And
And I tell you that, you know, I'm going to get to that.
Yeah.
Okay, so it turns out that when you do the physics and you look at the solar spectrum,
Yeah.
the ideal band gap, if you calculate on a piece of paper with all mathematical model, is 1.4 to 1.6 EV. That's ideal. 1.1 is non-ideal band gap.
So you want a higher, but
Well, we want higher, and I tell you why.
okay.
Because we want more voltage out. Okay, so you like to observe. Okay, so what happens that, okay, so imagine that when the photon is going in and it is exciting the electron and the spectrum, the maximum, I don't have a picture here of the solar spectrum.
Okay.
The solar spectrum energy is lot better around 1.4 to 1.6 eV if you take a band gap like that, okay? And when it is 1.1 eV, lots of electrons come out, they are hot electrons. That energy just goes through the materials and it gets lost by actually thermal energy rather than making electricity. If I take 1.5 eV, say, I get 1.5 eV electron volt, right? Energy is higher. For the same 1 electron, I get higher voltage. It means to get 110 volt, I need less number of electrons, right?
Okay.
Right? So that's one part. That's one of the main reason and also one has to see in the solar spectrum that how the solar spectrum looks like as far as the distribution is concerned, where you have the sweet spot. It turns out the sweet spot is between 1.4 to 1.6 eV. This material happened to be even better for that reason also.
1.9 or 1.8.
Right, so I could show you that. It's actually, we could tune that properties. Once you get to that, I show you the numbers there.
I'm sorry, it's totally misbehaving. I
Okay, so you
tried
could do this.
several things here.
Maybe it's not worth it. I'll tell you my.
Okay, so the part is
qualification-
that a solar energy, our photovoltaic panels right now, I have actually at home also,
Good.
is about 20% efficient.
Right.
So I feel very happy that I have 4 kilowatts of power. I don't pay any PG&E any bill. Really, I don't pay any bill. Okay. I need about 3 kilowatts. I put a little 1,000 watt more, and the result is that I have more power than I need, and as a result, I don't pay anything. Okay. So I'm very happy. But if I think scientifically, I say that all I did is using only 20% of the solar energy into electricity. What happened to my 80% which I'm throwing it away? I'm not worrying about it right now because I get 20%, I'm very happy with it. I like to see that at least I get 50% conversion efficiency. The same solar panel with the same area will give me 2.5 times more electricity. Remember, I'm not even 50% level, I'm only 20% in the silicon. How could I get to 50%? As a matter of fact, it turns out that the theoretical limit is 68%. Theoretical limit. If you make many layers of optimize all the band gaps and everything else, I should be able to get to 68%.
That means a third of its is that infrared that's being thrown away.
No, but what then I'm doing is that I'm combining many layers together. Some absorb at this a energy scale, the other absorb in this one, another absorb this one. So I'm making sure that I get all those extra energy there. So the view graph didn't come up, but it turns out that when you do this kind of research, so one of the things is that also by doping and all that, many times you could adjust some of the band gaps.
Well, let me rephrase something so I think I understand. Even though I'm not using as much of the spectrum, I'm using that portion more efficiently because it's a single layer.
Also, yes,
Okay.
that's right. That's also another part of that. That was the main reason of saying why does your yield goes up for photoluminescence. Because of that reason, because it does not require another conservation, which in the material silicon has to be thick enough in microns or hundreds of micron, because it has to go through the scattering process to pick that momentum. Otherwise, absorption doesn't take place.
Got it.
Here, I don't need that scattering process. One layer, as far as energy is satisfied, energy conservation, which is there, then absorption takes place. Photon got absorbed and it produced the electron. All I have to make sure electron come out, it doesn't get recaptured, right? All I have to do is make sure that that aspect is there. Yes?
Yes, what I want to say is, well, gallium arsenide, for example, is a direct band gap material.
Also,
It has the right,
yes.
Gap of 1.4 electrovolts. So why would people, say use that molybdenum sulfide instead of, say, just gallium arsenide, which is already a direct band gap material with the right gap here.
Right. So the question is going to be economy, one, and the impurities and all that, which changes properties most of the time. Impurity comes into the play. So you have to see all those parts. The industry has not adopted. I thought even 5-10 years ago this will be the materials of the future, but it didn't get adopted. So it is really the many times what it comes down to is the practicality, that how much you could produce that class of material in a way where you are not hindered by some other complications. Industry adoption of a technology on the average is used to be maybe 15 years, got to 10 years, now it's better than 10 years. Some technology comes out right away, and many of them, they just get stuck still.
But it's also true to say that the smaller layer cannot be just a freestanding layer. It has to be on top of something, right?
In this case, it was prepared on the top of a graphene.
Okay.
So there's already devices made out of these 2D materials, which are working devices, already made. Scientists already. How many papers are there? If you Google, if you actually go to Web of Science, I would say 2D materials, you will find out maybe as much as 100,000 papers written in the last 7 years. It's that much. Everybody, every review I go there, the first thing they say, we are going into 2D materials. Everybody says that. When I produced this paper, we wanted to have a science highlight. My colleague was saying that it is going to be useless. You are talking about single monolayers. How the hell you are going to make anything out of it? Because it's just one atom thick. Okay? And that was totally wrong comments.
So do we know exactly the role of that graphene or graphite?
We understand enough to say that it is in this particular measurement, it didn't play a role. We know enough. And that was one of the main thing to get it to the Nature Nanotechnology. We sent to Nature, right? Oh, it's very specialized. So you sent to Nature Nanotechnology. It is actually the next good one. And that was one of the questions we had to satisfy.
I'll ask if there's not another question. I think we should wind up, but if you don't mind, we'll take questions maybe out in the hall. But I did have one more on the 2D surfaces. You had a little diagram of thin Legos stacks.
Yes.
Do you want to talk about the work
Yeah.
done on multiple layers of these?
So the one of them, I could mention one of them. One of them very nice material is iron sulfide on strontium titanate. Iron sulfide on strontium titanate is a revolutionary material. Okay, iron sulfide, if you make a bulk material, it has a superconducting temperature of 7 Kelvin. That's a superconducting temperature. If you take iron selenide at a single layer and take a strontium titanate as a substrate, which means bulk, and put this iron selenide on the top of it, the material as a thin film has a superconductivity temperature goes up by a factor of 10 to 70 Kelvin. Nature paper 2 years ago, one of my colleagues did that. Okay? 10 times higher superconductivity temperature because of making this interface. And in the paper, the justification was it is because of the phonon which get created at the interface are helping it out and doping the material in some way and helping out the superconductivity. So that's one part. You take two insulators, combine them together, two insulators. Interface could be metallic or it could be even superconducting. And you could take heterostructure of many kinds and then you get into that one. So many times I told students, if you could make an iron selenide, single layer, iron selenide, strontium titanate, iron selenide, strontium titanate, superconductivity temperature will go up. Maybe at room temperature, but can you make it? So I actually, for the last 2 years, I have been telling students, go and make that material. You are going to be absolutely breaking a revolution. You don't know, you may be the guy who's making room temperature superconductor. There is a problem in making it. To prepare strontium titanate, you have to heat up to a certain temperature. At that temperature, iron selenide decompose. So those kind of complications come into play.
Wonderful. That's very interesting. Thank you.